This is Electric Universe Eyes, and today I'm going to narrate a post on National Geographic titled, Record-Breaking Lightning as Long as Kansas Spotted. One evening while working, Michael Peterson found himself staring at an enormous spider, but Peterson, a remote sensing scientist at Los Alamos National Laboratory, wasn't looking at a critter of the eight-legged variety. Instead, the form crawling across his screen was a monstrous flash of so-called spider lightning, a twisting network of light stretching hundreds of miles across stormy skies. Quote, "I was just blown away," he says. This map shows the largest lightning flash spotted in the satellite data. Its footprint extended across 44,400 square miles across multiple states. The bar along the bottom shows how the energies and sizes of the individual pulses change over time. His analysis revealed two record-breaking lightning flashes, the longest by length and by duration. One stretched over Brazil some 418 miles from tip to tail, slightly longer than Kansas is across. The second lit up skies for 13.5 seconds over the central United States. A third lightning flash over the southern United States sprawled some 44,400 square miles, nearly the area of Ohio. Official data aren't kept for the flash with the largest area, so it's not possible to determine if it set a record. The previous record-holding flashes, quote, called into question our typical view of lightning, end quote, Peterson says, but these latest mega flashes, quote, are now essentially pushing the boundary further for what lightning can be, end quote. What's more, the identification of such large flashes of light demonstrates the power of NOAA's newest weather satellites, GOES-16 and GOES-17, and the data is proving ground for Peterson's new automated processing system, published recently in the Journal of Geophysical Research Atmospheres, which tackles the most complex lightning data beamed back from space. These eyes in the sky will help us not only better understand meteorological hazards, but also long-term patterns in weather, tightening researchers' grasp on the links between storm evolution and our changing climate. Quote, lightning science is relatively new, and we're moving basically as quickly as we can get instruments to detect, says Kristen Calhoun, a research scientist at the NOAA National Severe Storms Laboratory, who is not part of the new study. The data from these satellites will, quote, give us an opportunity to study lightning in a way we've never been able to see before, end quote. Lightning anatomy. The events highlighted in this latest study are what's known as spider lightning. While you may envision lightning as largely vertical, spider lightning races horizontally through the clouds. It tends to form in the trailing zone of large complex storm systems. Such events form due to instability in the atmosphere, often when warm, wet air collides with cool, dry air, boosting the warm air into the sky. As the air rises, its temperature plunges, causing droplets of condensation and eventually shards of ice to form. All these bits, ice shards, droplets, and the slushy ice between, jostle for position. This causes some to gain a positive charge and others a negative one, each collecting in different zones of the system. Such separation, quote, charges the cloud, readying it for lightning. Within the rising cloud, the icy particulate is dense, which means collisions are frequent and the system quickly charges and discharges in mostly vertical lightning. But further away from this volatile zone is a more stable area known as the stratiform region. Here, the charge builds slowly over a much broader area. That means when lightning finally crackles across the sky, it's colossal. Describing one of the flashes recorded in the latest study, Calhoun marvels, quote, it taps into a charge that's in eastern Texas all the way into southern Arkansas in the same 10-second time period, end quote. Data overload. For the new analysis, Peterson turned to data collected across the Americas in 2018 by the GOES-16 and GOES-17 satellites, which zip around some 22,000 miles above the ground. They sit in what's known as geostationary orbit, meaning they're locked in a dance with Earth's rotation so perfectly timed that, if viewed from the planet's surface, the pair appear frozen in the sky. The duo is equipped with the Geostationary Lightning Mapper, or called GLM, which is in essence a fancy video camera that records photons in a very narrow range of frequencies at 550 frames per second. The two satellites continually watch nearly half of the globe, from eastern Australia to Africa's west coast, providing unprecedented amounts of information about the planet. In 2018 alone, the system recorded some 360 million lightning flashes across the Americas, beaming back data to ground-based processors that crunch numbers in real time. Still, it's not perfect. Quote, "The biggest challenge is also the biggest benefit," Peterson says. "It's just the sheer amount of data," end quote. Because of this real-time data feed, lightning can become too complex for the processing system. When that happens, the algorithm chops the flash into a series of snapshots. It then flags the broken flashes as degraded, so many researchers discard them during analysis. This was the case for around 4% of the 2018 data, which equates to some 14.4 million events. Or as Peterson puts it, quote, "essentially as many lightning flashes as we saw for the entire mission of the previous generation satellites," end quote. Peterson's automated method pieces the glowing jigsaw back together. The result? Spidery, multi-limbed flashes of lightning. While the record-breaking flashes he discovered still require official certification by the United Nations World Meteorological Organization, they both roughly doubled the past record holders. In 2007, a flash 200 miles long stretched over Oklahoma, and in 2012, a 7.74-second-long flash lit up skies over southern France. Flash forward. Quote, "At first glance, it looks pretty impressive to me what's been done here to really pull out things that were not fully represented in the operational data stream," says Edward Mansell, a physical scientist at the NOAA's Saphir Storms Laboratory. Calhoun agrees, noting that the latest work demonstrates just how active storms can be. But she also cautions that determining whether lightning is occurring in a single flash, as opposed to a couple in rapid succession, is tricky business. As lightning propagates, it deposits some of its charge, she explains, which changes the electric field and can often spark a second flash. A lightning baby then starts growing across the sky. Quote, "When you're looking at an optics sensor like GLM, you won't be able to see that break," she says. Ground-based systems like the one that identified the past record-holding lightning monitors for radiation in a swath of the sky and charts high-resolution, three-dimensional lightning maps. But such systems are more limited in their range than satellites, Peterson says. A combination of both methods will likely provide the best look into lightning structure and physics. Still, the latest study not only offers an exciting peek into the vast untapped data streaming back to our planet, it raises important questions about lightning safety. These monster flashes arrive after it appears to people on the ground that the storm has subsided, Peterson notes. It may no longer be raining, perhaps the lightning has paused, but then a spidery beast could suddenly scurry across the sky, crossing state borders in a matter of seconds. It's vital to understand just how volatile storm clouds are, Calhoun adds. Quote, "Even if you don't see lightning happening, there could be a lot of activity going on above you."